4. The question is, okay, let's quickly start. Calcium nitride, he says that it reacts with water, so write an equation. So calcium nitride reacts with water and we don't know what's going to happen. Okay, maybe they gave, he says that there's a white precipitate and an alkaline solution. So the alkaline solution, the only possible alkali that's going to be formed is going to be calcium hydroxide. I think that's the only one that's possible in this case. So they said that it's going to form an alkaline solution, and so that's calcium hydroxide. And the other thing is that the oxidation number of nitrogen does not change. So what is happening to nitrogen? Can anyone guess the oxidation number of nitrogen? So there is something else that is going to be produced, and the oxidation number of nitrogen does not change. So pehle to guess.
Ammonia.
Okay, that's going to be ammonia. And the reason it's going to be ammonia is that N over here is -3 because it's an ionic compound. Calcium is +2, N is -3. And over here, N is also -3. The oxidation state is -3. So that is the correct answer. And you have to balance this. So this would be 2NH3 and 3 calcium hydroxides and 6 water molecules, I guess. The next one is that the enthalpy of solution of the hydroxides of the group 2 elements become less endothermic down the group state and explain the trend in the solubility of group 2 hydroxides. So what happens to group 2 hydroxides? They become more soluble down the group. Like magnesium hydroxide, dissolving it is... so again, it's a typical question. If you want to dissolve a hydroxide, the ions must dissociate and they should turn aqueous. They should get scattered in water. An ionic lattice would break and two things would happen. Okay, if you have Mg NaCl dissolving, just a second. So this is, remember, dissolving an ionic substance is something like this should happen. That two things will happen. The first thing is that the lattice is going to break. The positive and negative ions, that's the opposite of lattice energy, that the lattice, ionic lattice would break and the ions would then get hydrated. They would make bonds with water molecules. The water molecules are going to come and they're going to stick to the ions. So two steps would happen. The lattice would break, MgOH2, so it would break into gaseous ions. The ions would separate, the ionic bonds are going to break. So that is the negative of lattice energy, that's bond breaking. So this part is endothermic. And then they're going to make bonds with water molecules. That's the enthalpy change of hydration. So that is delta H hydration and that part is exothermic. So he's saying that down the group, the enthalpy change of solution is becoming, this overall thing is enthalpy change of solution. So it's becoming more endothermic. So what happens is, always it's the same answer, that down the group, the cationic radius increases. I mean, that's the first point, that down the group, when you move down the group in group 2, the cationic radius increases, which is why the enthalpy change of hydration and lattice energy, they both decrease because they're going to make weaker bonds. And lattice energy both decrease. So because you have bigger ions, weaker bonds, so this is decreasing. It's easier to break the lattice if you have a bigger ion, and weaker bonds are going to be formed. So this is also going to decrease. So both values are going to decrease down the group. But since the overall enthalpy of solution is becoming less endothermic, that means the endothermic part is decreasing more compared to the exothermic part. So, so the last point would be, that's point number 1. Point number 2, the last point would be that enthalpy, lattice energy, which is the endothermic part, decreases more compared to compared to the enthalpy change of hydration. Because overall it's becoming, they've already told us that it's becoming less endothermic. So remember this one, okay? It's a very typical question that always comes. Make sure you remember this, how to answer this one. Okay, you clear? Is this clear? And the other question is about sulfates. And sulfates, they become less soluble down the group. In that case, the same thing happens. Sulfates, when they dissolve, down the group, lattice energy decreases as well as hydration decreasing as well. Both of them decrease. But in that case, sulfates become more insoluble. That means overall enthalpy of solution is becoming more endothermic. So this decreases less compared to this one. So in that case, lattice energy would decrease more compared to enthalpy change of hydration. And he's asking for the same cycle to be drawn over here, which we have already done. So he's saying label this. So what happens when gaseous ions turn into aqueous ions? That's enthalpy change of hydration. What happens when an ionic gaseous ions turn into an ionic solid? That is lattice energy. And what happens when ionic solid turns directly into aqueous ions? That's enthalpy change of solution. Okay. So is this part clear? And remember, this question appears in every, I mean, this one specifically, almost in every paper. Is that clear?
Yes, sir.
Sign clear?
Yes, sir.
So this one, now it's about KSP. What is KSP? That you have, KSP is the equilibrium constant of something dissolving, an ionic compound dissolving in a saturated solution. So when you dissolve KAF to solid, what will happen is it will dissociate into aqueous ions. It will form calcium +2 ions and it will form 2 fluorine -1 ions. But in a saturated solution, the more you dissolve, the more precipitate it's going to form, because there's a limit beyond which a solution will not, more salt or more aqueous ions are not going to be produced. So it's going to be at equilibrium once it's saturated. So you have to give the KSP value, write an expression for the KSP value. It's going to be product concentration. So it's going to be calcium ion concentration and fluorine ion concentration. That's going to be squared, divided by the reactant concentration. The reactant is a solid, and that's taken as a constant, so you don't write that. So this is the KSP value. You have to write the units. So it's concentration into concentration squared. So concentration. So it's concentration cubed. So which is basically mole per dm cubed. And that would give me mole 3 and dm -9. And he's given me the KSP value. That is also provided already. So it's already given. So he's asking about the solubility of calcium fluoride. When he refers to solubility, what he means by that term is what is the concentration of calcium fluoride and how much of it dissolves. So we don't know what the amount is. We just know that calcium fluoride is dissolving. So I'm going to take that as X. I'm going to assume that X mole per dm cube dissolves. So according to that, the amount of calcium ions that are going to be produced are going to be X mole per dm cube. And the amount of fluoride ions that are going to be produced are going to be 2X mole per dm cube. So X is my solubility. Solubility is how much of calcium fluoride is actually dissolving in the saturated solution. So I've taken that as X. And I'm going to substitute these values into this expression. So the KSP value is already with us. It's 3.45 times 10 power minus 11. So the KSP value is already with us. Calcium ion concentration is X mole per dm cube. And fluorine ion concentration is 2X mole per dm cube. So it's going to be X mole per dm cube into 2X mole per dm cube, and that's going to be squared as well. And from this expression, Okay, I just substitute this into this expression and the value over here in KSP. And from this, I'm going to figure out what X is. So X would be, come on, it's 4X cubed. So can anyone do the math and tell me what the answer is? So what do we get for X?
2.01 into 10's power minus 4.
Okay, that's your value. TK score. We can check the answer.
805.
ठीक है, राउंड साइड ही क्या था? 2.05.
नहीं, yeah, 2.05.
ठीक है. So that's 2.05. So just remember that KSP, you always get a typical question of KSP. Either they're asking you to calculate KSP, the solubility is given. So you'll find the concentration of the ions, you'll put that in the expression, you'll find KSP. Or you'll get the opposite question, which is that KSP would be given and they'll be asking you to figure out how much calcium fluoride actually dissolves. And you could just going to take it as X. So you'll find the concentration of the ions in terms of X. Put that concentration in the expression, and once you do that, you'll be able to figure out what X is. Now, the next one is about explaining why thermal stability of the group 2 nitrates increases down the group. So carbonates and nitrates become more stable. And the reason for that is that, I'll explain this using a carbonate. Let's talk about a carbonate first. And the reason for that is that if you have a smaller ion has more polarizing power. Let's say you have magnesium ion. Magnesium carbonate would be easily, the carbonate ion would be very polarized because the magnesium ion would be very strongly attracting the oxygen ion. And it would end up forming carbon dioxide, and this thing would form MgO. The carbonate ion would decompose. But on the other hand, if you have a bigger ion, like let's say barium ion, it's going to be more stable. Barium ion is going to be bigger in size, so the charge density is going to be lesser. So the attraction for the electrons in the carbonate would be less. So the carbonate ion would become more stable. It's not going to get polarized. So that's the only thing you have to mention over here, that down the group. So what you'll mention is.
So can you explain this? This charge thing.
So carbonates की stability का ये कि if you have a carbonate and nitrates as well, a smaller ion has greater charge density, right? If you have a +2 charge on a smaller ion and you have a +2 charge on a bigger ion, the +2 ion has a much stronger attraction. ये तो clear है, is that clear? So what it will do is it will polarize the carbonate ion. I mean, the oxygen is right now sharing electrons with carbon, right? So instead, what will happen is that the oxygen over here, the electrons over here will get attracted to this thing, Mg+2, and MgO would be formed. Okay, and this bond would break. Is that clear?
Yeah.
So the carbonate would decompose very easily. The carbon dioxide would escape and the oxygen would bond with the magnesium, which is +2. Over here, if you have a bigger ion, there's going to be less attraction. So this bigger ion, let's say that's a barium ion. Down the group, the ionic radius increases. So the bigger ion is not going to pull the electrons in the carbonate ion towards itself. So the carbonate ion would kind of remain intact, and it will be harder to break its bonds. Is that clear? So what you have to write is down the group. That's the first thing. Ionic radius increases, or cationic radius increases. So what happens is charge density decreases. So your charge density decreases, and polarizing power decreases as well. So the carbonate ion becomes more stable. And the last thing is that the carbonate ion would become more stable. We can just quickly check what the wording was. Ionic radius increases, that's 1 mark, and less polarization or distortion of the nitrate ion. Sorry, we were talking about the carbonate ion, but less distortion or less polarization of the nitrate ion. That's about it. So the next one, you've got a moles question. The student analyzed a sample of sodium nitrite by titration with cerium 4 ions, this one. So, and the equation is given. So the purpose, I don't know what the purpose of this whole thing is, but he's saying that 0.138 grams of impure sodium nitrite. So most of these nitrite ions are coming from sodium nitrite, right? So I'll just figure out the moles of, if you have, actually I can't figure out the moles because it's impure. So you've got 0.138 grams of impure sodium nitrite. So you can't figure out the moles of this thing, right? And he's saying that it's dissolved in water and made up to 100 cm3 in a volumetric flask. So this thing is mixed in water in a volumetric flask, and it's now in the form of a 100 cm3 solution, right? And it contains this is actually nitrite. So it contains nitrite ions. So that's one thing, 0.138 grams dissolved in 100 cm3. Now, out of that 100 cm3 flask, 25 cm3 of this solution was taken out. So into a volumetric flask. So 25 cm3 of this solution that contains nitrite ions coming from sodium nitrite, right? It's taken out and it's titrated with Ce4 plus ions. So Ce4 plus ions are falling from the top from a burette. And he says that 21, so the amount of Ce4 plus 1 is given as well. So the volume is given and the concentration is given. So you can figure out moles. If you know the volume and concentration, it's moles is concentration times volume. So if you do that, it's going to be 21.8, right? Multiplied by 0.04. And this should be divided by 1,000. Kitne moles bane? How many moles do you get for this?
(8.72 10 power minus 4).
So this one, you've gotten 8.7 2
7.4 7.2, yes.
10 power minus 4 moles, right? So according to the ratio, the amount of nitrite ions would be half of that, right? So this is 8.72 into 10 power minus 4. So what is half of that? The amount of nitrite ions are, it's 2:1. So how many nitrite ions do you get? What is half of this?
4.36.
4.36?
Yes, Jason.
So you're going to get 4.36 times 10 power minus 4, right? Now, the next part is, so they didn't give any steps. They just asked you to figure out everything on your own. So there are no steps. It's just a 3-mark question. So you found the nitrite ions moles, 25 cm3. So what would be the moles in 100 cm3? That's going to be 4 times greater, right? So the moles over here would be 4.36 times 10 power minus 4, and that's going to be multiplied by 4, because in the 25 cm3 sample, you're getting this much. So in 100 cm3, the original sample, where you have added all of this, you're going to get this much moles. So how many moles do you have?
1.74 10 power minus 3.
So the exact moles 1.74 into 10 power minus 3, right?
Yeah.
So these are your exact moles of sodium nitrite. Remember, this is impure. This is the wrong mass. So we'll calculate the exact mass now. We'll multiply it by the MR, and we'll know the exact mass in the impure sample, which is going to be, the MR would be 23 plus There's a nitrogen, that's 14 plus 2 oxygens, that's 32. So what is the exact, what is the exact mass?
0.12 grams.
So it's coming out to be 0. So the exact mass is coming out to be 0.123 significant figures, 120 grams, right? I'm assuming it's 120 grams.
Yeah.
And now you can figure out the per stage purity. The per stage purity is that in this sample, there's 0.12 grams. So it's 0.12 divided by 0.138 times 100. And you'll figure out the percentage purity. So what do you get for this?
87%.
Remember 3 significant figures. So, I mean, like over here, it's 86.96 given. I mean, you can round it off to 87. It's, but let me just quickly check. It's everything is 4 significant. This is 3 significant figures. So the answer preferably should be in 3 up to 3 significant. That's going to be 87.0%.
So यहाँ पे we have a couple of values जो 3 significant figures में और then there are values which are to 4 significant figures. How do we?
So if you're multiplying and dividing, okay, so the uncertainty is on the 4th one because of this. But the fourth number is now uncertain because you don't know if it's 25.01 or 25.02 or what's coming after 25.0. So the 4th one becomes uncertain. Is that clear?
I mean, uncertain.
But yeah, like if I have 4.12 a number, okay, and I have another number which is 2.0, and if I multiply them, so my answer, this is 3 significant figures, that is 2 significant figures, okay? So my answer would be, well, let me make it easier. Let's take this as 4.00. The point I'm trying to make is the answer is accurate in multiplication and division. The answer is accurate up till the least significant figure number. Okay, if this is 2 and this is 3 significant figures, so your answer is going to come out to be 8, but it's going to be 8.0. It will be accurate up till 2 significant figures because there's going to be doubt on the 3rd one because you don't know what this is, what's coming after this one. So when you multiply this, the 3rd number becomes doubtful. Is that clear?
Yes, sir.
Or uspe yaad rakha ki when you're adding and subtracting, the answer is accurate up till the least decimal place. Like if I have this number, and I'm adding the 2 numbers together. So what am I going to get? I'm going to get 3.1. Now 2.3 is uncertain because I don't know what this is. Is that clear?
Yes.
So just remember this. It's a very not. I mean, you don't have to be that careful about this. I mean, ek to ye yaad rakha ki if the values are given up till 3 significant figures or 4 significant figures, make sure your answer is accurate up till the least significant figure value. They're going to cut marks if you go beyond that. If you go beyond that, they haven't written this over here, but in a lot of marking schemes, they do write about the significant figures as well. So, but just be careful about this. This thing, and usually there is no addition subtraction. I mean, in moles question in chemistry, there's always multiplication. So you don't even have to remember this. So yahan pe it's least significant figures, over there it's the least decimal place accuracy. Now the other thing is there's acidified magnate ions, and he's saying it can be used to analyze solutions containing nitrite ions by titration in acidic solution. NO2 ions exist as HNO2. Use the data booklet to construct an ionic equation. First thing, acidified magnate 7 ions. So there's a reaction that's happening. So I'm going to just do the working on the data booklet. And let me open the data booklet. I said, remember, he's talking about magnate 7 ions acidified reacting. So you open the data booklet, which would be now given with the question. And you're going to look for acidified magnate 7 ions. Magnate 7 is MnO4 minus 1. So there is this one. That's magnate 7 ions acidified. That's another one. And I don't think I have magnate ions over here, but not acidified. So I'm going to leave that. So these two are my prime equations. And right answer, this one. And the other one is there's a titration that's happening. The reaction is happening with nitrite ions in acidic solution. And he's saying the NO2 ions exist as HNO2. So we're looking for equations in acidic solution of HNO2. So I'll open the data booklet and I'll find equations involving HNO2. That's one. And I think that's the only one. There is no other equation where HNO2 is involved. So that's it. I'm dealing with 3 possible reactions. So what's the rule? The higher potential out of the 3, the higher potential gains electrons and the lower potential ends up losing electrons. So out of the 3,
1.67.
The lowest one loses electrons, right? I mean, that's the rule. So the lowest one is going to lose electrons. It's going to go in the backward direction. And the higher one is going to gain electron. It's going to go in the forward direction. And it's going to gain electrons. And this is what's going to happen. And that's going to be your equation. And let me write the equation. And it's actually going to be the wrong one. I'm going to explain why, what is the correct equation. We'll check the marking scheme later, but let's do this process first. How do you write the equation? Add up the reactants. So you're going to add up the reactants. Make sure the number of electrons gained and lost are equal. So you'll multiply this by 3, the whole equation. You'll multiply this equation by 2 so that the number of electrons gained and lost are equal. You're going to add up the reactants and you're going to add up the products. That's going to be your reaction. So the reactants in the first one is 2MnO4 minus 1, 8H plus 1, and 6 electrons. So it's 8 MnO4 minus 1. No, sorry, 2 MnO4 minus 1. That's it. I don't know what's happening. That's it. 2 MnO4 minus 1 plus 8H plus 1 plus 6 electrons. And the reactant over here is HNO2, and that should be multiplied by 3. So it's going to be 3 HNO2 plus 3 H2O. And the products are going to be the first one. The product is multiplying by 2 MnO2 and 4 H2O. So that's 2 MnO2 plus 4 H2O. And the second one, the product is 3 nitrate ions. And what else? 9 H plus 1 ions. Okay, that's about it. And you're going to simplify this. The 3 water molecules are going to get canceled out. You'll be left with 1 on the right side, just like a math equation. 8H plus 1, 9H plus 1. So that's going to get canceled out as well. And you're going to get this thing. And that's your equation. But based on our rules, I mean, we've done this perfectly fine. I mean, this is exactly what the reaction is going to be. But I'll check the marking scheme. This is probably not going to be the answer. I said the answer is Mn2 plus. Now, the reason why it's Mn2 plus, there's a lengthy way of understanding that, and there's a shorter, simpler way of understanding that. Make sure whatever you've done this correctly. There's nothing wrong with this. The shortcut is whenever you get acidified MnO4, go for the 1.52 equation.
Yeah.
Go for the 1.52 equation. I mean, that's a simple shortcut. Like if you, without understanding, if you want to know, just make it a point for MnO4 minus 1. Acidified whenever you have this equation, instead of this equation, go for this equation, and that will give you the right answer. Now, I'll give you
what will
हाँ
आपने क्या कहा
नहीं मैंने कहा the shortcut
जी
मैंने कहा कि shortcut ये है कि without going into a lot of detail and by saving your time, the shortcut is कि, I mean, I explained that there's nothing wrong with this. Whatever we did was we did correctly. ठीक है? The shortcut is that whenever you're dealing with the MnO4 equation and this one is gaining electrons, instead of choosing this equation, choose this one. That's the shortcut.
Because it's more.
क्यों
अच्छा, and better the shortcut. ठीक है, without any understanding, that's the shortcut. ठीक है, go for this equation. ठीक है, that is exactly what they have done as well. And I'll give you a reason for that. ठीक है, I'll explain this. The explanation is pretty lengthy. So they're turning it into Mn2 plus. So they've actually gone for this equation instead of our equation. Now the lengthier explanation. The lengthier explanation is what we did was not wrong. What we did was just the first step. It was step 1 of the reaction. It's a multi-step reaction. Once MnO4 turns into MnO2, there's going to be a second reaction. What will happen is this MnO2 over here, I'm going to mark it in red. So let's focus on what we've done. The MnO4 changes into MnO2. And this MnO2 acidified is now going to react with this further. This MnO2 acidified, there's going to be a second step. And the product that is formed over here, the acidified MnO2, it will go and react with our nitric acid again. That's going to be the higher potential, that's going to gain electrons. And this one is the one that's the lower potential, that's the one that's going to lose electrons. So once the first step has happened, you have acidified MnO2, you have H+1, and you've got MnO2. And that will again further react with nitric acid. It's going to be the lower potential, so it's going to lose electrons again. And MnO2 acidified is going to, so at this point, there's going to be a second step. So step number 2 would be, so I'm going to draw the step number 2 now. And in this case, the number of electrons gain and loss are already equal. So what I'm going to do is, I'm just going to write the reactants. The reactants are HNO2 over here and water. So I don't think I need to, the electrons over here and over here are already equal. The reactant over here is MnO2 plus 4H plus 1. And the product over here is Mn2 plus 2H2O. And the product in this bottom one is NO3 minus 1 plus.
Sir,
Hanji.
why would MnO2 react again?
Because once MnO2 is formed, MnO2 is still has a higher potential compared to this nitrous acid. I mean, this is the lower potential. So let's assume the first reaction has already happened. So if there is more nitrous acid, that nitrous acid will react with the MnO2 because that is the higher potential. It's going to gain electrons, and the nitrous acid would again lose electrons. So there's going to be a further reaction between, I mean, you had the first reaction of HNO2 with MnO4 and MnO2 was produced, but the MnO2 ended up reacting with HNO2 again. So there's going to be a further reaction. Is that clear?
Yes,
Yes,
sir.
sir.
So there's going to, so the point is there's actually 2 steps to the reaction. The reaction will happen further. And the reaction will stop now. Will the Mn2 plus further react? The Mn2 plus, let's focus on that. No, it's not going to react with nitrous acid. Why? Because it no longer is the higher potential. This one was, the nitrous acid one was the lower potential, so it was losing electrons, right? but it will not be able to react with it. It will not be able to lose electrons. Why? Because that is not able to gain electrons. It's got a very low potential. So the reaction will stop at Mn2+. Is that clear?
Yes, sir.
As long as it can gain electrons, it will continue to react as well.
Yeah, it will continue.
I mean,
And this specifically happens for elements that have too many oxidation states. Like Mn over here has a lot of oxidation states. So,
yeah.
I mean, there was a reaction of iodine with B3+, I think. There was a reaction of Fe3+ with vanadium. So there was another reaction like this. You had Fe3+, that was the higher potential, not this one. There was a reaction of Fe3+, this one. And it came out to be the higher potential. And so higher potential gains electrons, right? So it's gaining electrons, and it was reacting with vanadium. Vanadium happened to be the lower potential, that's minus 1.2. So it happened to be the lower potential. So it turned into V2+. But once it turned into V2+, it's still the lower potential. So it would lose electrons again. And remember, he's reacting it with Fe. Fe is 0.77 volts. So as long as Fe is the higher potential, Fe would continue to gain electrons. And as long as vanadium is the lower potential, vanadium would lose electrons. It's still lower compared to 0.77. It's still lower compared to 0.77. It turns into V3+, then V3+ again lower than 0.77, so it would lose electrons further. And then you reach VO2+, then the reaction would stop. Because now it's no longer the lower potential.
Thank you. I had a question like that, and I was wondering what was happening. Thanks.
Yeah, so just remember, the shortcut for this one is, the shortcut for this MnO4 thing is, whenever by any chance you get this 1.67 volts, don't use that equation, use this one directly. So that will save you a lot of time. I mean, you don't have to do all of this.
I mean, use 1.52 as highest potential.
Use that instead of 1.67. So in that way, okay, at the end of the day, it is forming Mn2+, right? But it's happening in 2 steps. You'll just avoid the extra working.
So what about the acidity of those? I mean, of those 2 questions, does it matter or it doesn't matter?
Which one?
To look at it, the acidity. That one it has 8, and the other one is 4. You know, the one that you
no,
said
that doesn't really matter. It's going to come out to be the same thing. Like if you add step 1 and step 2, you're going to get the same equation if you had selected 1.52 initially.
Or I meant just for selection. But I mean, when you look at this acidity, just to look at which you can go
because he's using the term acidified, you have to go for acidified MnO4 -1.
Okay.
This is not even in the contention. Even if you choose this one, there's another MnO4 -1 equation, right? But that's not even the highest potential. So that's very far away. So you're going to reject that anyways. So just a second. So remember these chain reactions for MnO4 -1 acidified. The simple thing is, just a second. I think my laptop has stopped. So it's here. So just remember, and there are a couple of more reactions. I'll do another one. For example, there's another reaction of I think tin with iodine, right? So what happens is tin is somewhere over here. So I'll just quickly explain what will happen with tin with iodine. It's going to be a chain reaction. It's going to be multiple steps. Tin is this one. So that's your equation, right, for tin. And iodine is not given on this page. So I'm just going to write iodine. That's 2I -1, and that's 0.54 volts. So tin clearly is the lower potential, right? And this clearly is the higher potential. So what will happen is the higher potential gains electrons, right? Tin ends up losing electrons, right? So that's the first reaction. The first reaction would be tin, that's the reactant, and iodine react. And when they react, tin 2+ is formed. In the first one, tin 2+ is formed. This gains electrons to form 2I -1. But then tin 2+ is formed. Now, once tin 2 plus is formed, that's still the lower potential compared to iodine. Like compare this with tin 2 plus with iodine, it's still the lower potential. So tin 2 plus would lose electrons again. As long as iodine is the higher potential, iodine would continue to gain electrons. So the second step would be, there's going to be another reaction. Tin 2 plus would lose electrons again to form tin 4 plus. And iodine would again gain electrons. So the overall reaction would be, you've got two steps. So the basic idea is, iodine will continue to oxidize this. It will continue to lose electrons as long as it's the lower potential. And you only have to watch out for this if you have elements that have many oxidation states. For example, lead over here. You have to watch out for that. For Mn, you definitely have to watch out for. Usually doesn't happen with other elements, but like chromium over here, you can watch out for that as well. Like if something is reacting with chromium, and chromium is the one that's losing electrons, that's the lower potential. And let's say it's reacting with something that has a very high potential. I'm going to take, I think S2O8. So it's got a very high potential. So this S2O8 thing will continue to gain electrons as long as chromium is the lower potential. So chromium would first lose electrons to form chromium 2 plus. Then it would, chromium 2 plus would lose electrons to form chromium 3 plus. Then chromium 3 plus would further lose electrons because it's still the lower potential, right? So it will continue to get oxidized as long as this other thing has the higher potential. S2O8. So is this part clear?
Yes, sir.
And we can just sum this up. It's we got the, I mean, I'll just look at the, we did both workings. Actually, in this case, the working that we did, the final step would be, the overall equation would be, you add the two reactions together. So that's a pretty lengthy process, but you're going to get the same thing if you had selected 1.52. I mean, right straight away you had selected this. So you would have gotten the same result, which is this one. And he's asking about the E0 cell. So the E0 cell is given as he has also taken 1.52. I mean, he's taken the 1.52 equation. So the E0 cell is coming out to be 0.58 volts. The E0 cell is the higher potential minus the lower potential. So it's 1.52, and the other one was the 0.94. So you subtract the difference. So instead of taking 1.67, take the 1.52 value. And what else is the question? Oh, no, it's not. Explain the difference between a strong acid and weak acids. You can kind of do that. It's a proton donor, fully ionizes, weakly dissociates, fully dissociates, weakly dissociates. And also remember, when you completely ionize, that's fine. Write an expression for the dissociation of HNO2. So HNO2 is going to dissociate. It's an acid. So acids are going to dissociate, and they're going to produce release an H+1. So what's the K expression? It's product concentration, which is H+1, NO2 -1 concentration divided by the reactant concentration, which in this case is HNO2. So that is the acid dissociation constant. The other way to write, Hanji.
The other way to write it is to as H square. Yeah.
But I think this would be the one that he's looking for actually in this case. But I guess
So,
that's the one.
How do we like know कि फिर वो लिखने की ये लिखना?
Hey, that's for math. Okay, like if you're doing some math, like in the next one you're doing some math, so that is fine. But he was specifically asking for the expression for HNO2, so you have to bring in the NO2. But even the shorter one is H+1 squared divided by the acid concentration, right? But that's, I mean, these are just used for mathematical calculation. So I mean, because he's looking for the expression, so this is the expression. So calculate the pH. So this one, you're going to use this one. It's calculate the pH. So the K value is given, it's 6.9 into 10⁻⁴. And your H+1 concentration, you have to find the H+1 concentration. And the acid concentration is given as 0.15. So you can do the math. You will get your answer, which is you're getting 2 over here. Anyways, once you find H, what is pH? pH is the minus log of the concentration of H+1 ions. And he's also talking about the percentage of HNO2 molecules that are ionized. So you can calculate that. Like once you have the H+1 concentration, that is the percentage of HNO2 because it's 1:1. So once you have the H+1 concentration, that's the amount of H+1 ions that are ionized. So out of 0.15 mole per dm cube, that will be the amount of H+1 that is ionized. So you can find the percentage. Is that clear as well?
Yes, sir.
Yes, sir.
Or so it's a big question. So we'll it's a 22-mark question. That's so we'll continue with this one. This is page 13. We'll continue with this in the next class then. Okay then.
Chalo, okay, sir. Allah Hafiz. Thank you.
Take care. Allah Hafiz.